Let's talk about the Baeyer-Villiger oxidation now. This is a way of synthesizing esters and carboxylic acids from ketones and aldehydes, respectively. The way the Baeyer-Villiger oxidation works is you combine a ketone or aldehyde along with a per acid. So remember synthesis of epoxides back at the beginning of the course, it's the same reagent we use to make epoxides. When these are combined, you're going to either get an ester and a carboxylic acid, or if R2 is a hydrogen, that means you started with an aldehyde and you get a carboxylic acid instead. The mechanism of this reaction is as follows. First, the oxidant of the per acid will add to the carbonyl group as a nucleophile. These things are not fantastic nucleophiles, but they are decent, so this reaction will proceed fairly quickly. This will produce this charged intermediate. Now, this is sort of an exception to our general rule of reactions, strong acid and base incompatibility. Since this process generally occurs in a neutral solution, this type of intermediate, though unstable, is actually the best experimentally observable way to explain how this reaction works. Because of the proximity of the carbonyl group to that proton, there's then an intramolecular proton transfer to give this carbonyl protonated intermediate here. Now, the next step kind of happens all at once, so make sure that you can follow all the arrows for this. The electrons from this negatively charged oxygen will come down, regenerating the carbonyl group. This will cause the R2 group to migrate over to this oxygen, ejecting the per acid, quenching the positive charge. So the core part of this is actually a rearrangement. The arrow that we're using to push R2 onto that oxygen is a rearrangement arrow. So what this gives is our product, which is an ester in this case, and then a carboxylic acid derived from our per acid. What's important about this reaction is to note the migration rate of different groups. They don't all migrate at the same speed. Here, protons migrate faster than tertiary carbons, which migrate faster than secondary carbons and phenyl groups, which are about equivalent. Those both migrate faster than primary groups, which migrate faster than methyl groups. So given these rules, we should be able to predict the Baeyer-Villiger oxidation products if given a starting ketone or aldehyde. So I want you to work through this with these three starting materials, an acyclic ketone, a cyclic ketone, and an aldehyde. And we're going to combine these with these per acids. Now here I've chosen three different reagents just to remind us that there's different ways we could write the per acid. MCPBA is a specific example of a per acid that's commonly used to form epoxides. RCO3H is a generic way of writing a per acid, and then the last one, MECO3H, is a specific example of a per acid that we just haven't talked about before. So go ahead and work through these problems. Note the product that's formed in each and which group will migrate faster under each circumstance. Pause the video here and then start it again when you're done. Alright, so this problem is really a matter of figuring out which group migrates the fastest. In the case of the first problem, we have a tertiary carbon on the left and a methyl group on the right. Since the tertiary carbon will migrate faster, that means that the isopropyl group will have a higher chance of being transformed into an ester over the methyl group. So it's the isopropyl ester that we're going to form when this reaction is done. In the case of the cyclic ketone, we have a secondary carbon on the left, a tertiary carbon on the right. As tertiary carbons migrate faster than secondary carbons, we're going to end up forming this cyclic ester, which is also known as a lactone. In the case of the aldehyde, the hydrogen is going to migrate faster than the tertiary carbon, meaning that we're going to end up with a carboxylic acid. That's all for the Baeyer-Villiger oxidation. In the next part, we'll talk about nomenclature of carboxylic acids and esters. This will mean that we're going to be leaving Chapter 19 and moving on to Chapter 20.